so guys, the thing is that if you might remember, we started off with the concept of operational amplifier, where we expected something out of it. We expected that an operational amplifier would give us a certain amount of gain to an input signal, and the signal would become bigger than the actual value. But the response of the operational amplifier naturally doesn't come out to be like that. And that happens because of the extremely high value of the gain, which is 10 to the power of 5, which is, as per the parameters of the operational amplifier, a very big number. And what actually happens is that instead of becoming a bigger number as an output, the output sort of flattens out and just gives us the two saturated modes of the output. So we wanted the output to increase proportionately, but it was not increasing proportionately. It was basically just going into either a positive saturation mode or a negative saturation mode, depending upon either the plus Vs is bigger or minus Vs is bigger, and that's how we were getting an output. So, but we still made use of operational amplifier, and we used it for a comparator circuit, which is a big use in terms of specifically when we did the second type of circuit, where we said that we can use temperature dependent circuit, and it's more of a thermostat where the AC compressor motor would switch on and off with the variation of temperature. But still, I mean, it was a use. It was a use in terms of a comparator circuit, but it's not what we actually wanted operational amplifier to do. In this particular section, we will see that we would have a control over the gain of an operational amplifier, and we would acquire that particular gain by connecting a feedback, or you could also say a negative feedback to the circuit. So we are going to connect a negative feedback, and a negative feedback means that when you have an output of an operational amplifier, and then some fraction of that output, some fraction of voltage of the output is connected back to the inverting input specifically. That's why it's called negative feedback. So when you connect some part of the output back to the inverting input, first up, that's called negative feedback. And what this negative feedback does, and we will see that in a while, but somehow what that negative feedback does is that it controls the gain of an operational amplifier. Not just that it controls the gain of an operational amplifier, it basically makes it possible for you to change the value gain, the value you would want. So you would be able to control that value gain and have the value gain of your own choice. First thing that I would want you to understand is what is negative feedback. So negative feedback is that when your output terminal in a certain way goes back into the inverting input terminal. In other words, that's exactly what's more important. That if examiner would ask you what's negative feedback, so you'd say when fraction of the output is converted back into the inverting input. So that's what negative feedback is. And there are two types of negative feedback circuits. One is inverting operational amplifier, and the other one's a non-inverting operational amplifier. So we will first talk about the inverting operational amplifier circuit. In that, what you actually do is that you connect two resistors between the output and the input, R1 and R2. And then right from the middle of that, you go back to the inverting terminal. And the non-inverting terminal is connected to ground earth. So if you see this kind of circuit, then that means that's an inverting operational amplifier circuit. There are, I mean, as far as negative feedback circuits are concerned, there are only two types of circuits. And then this is inverting operational amplifier, and then you would do another operational amplifier, which is non-inverting operational amplifier. And you would see that in non-inverting, I don't want to talk about that right now because that's another circuit I'll be doing later on. but you will notice the difference is that these two would switch with each other. So if V input goes there and the ground comes here, then that would be a non-inverting operational amplifier circuit. So guys, how does that control the gain of the operational amplifier? There are two ways to look at it. And one I think is a little longer method, but that makes you understand it more properly as compared to the other one. And I want you to understand both possible ways, both ways of understanding how operational amplifier controls the gain. So this is the one on the left, the more complicated way towards understanding that. So if I say that I have this inverting operational amplifier, this is the circuit, and so no matter what the circuit is, this is the output formula. The output is equal to A naught V plus minus V minus, where we always deal with ideal operational amplifiers. But we do know, I mean, for real operational amplifiers, the value of A naught is very high, that's 10 to the power 5. But for ideal operational amplifiers, we're going to take that value to be infinity. So we know that the value of A naught is going to be infinity, and this is the formula for the output. Okay, so this is the basic formula. So if I look at it very closely, I mean, look at what's the voltage in V minus and what's the voltage at V plus. So we can sort of figure that out. But before I do that, so the total voltage is E, this is R1, this is R2. If I'd say that the voltage across R1 is V1, so it's called potential divider rule, R1 plus R2 times the total voltage E. So I was trying to figure out that how this particular formula applies in this particular situation. So I look at the V plus voltage. So V plus voltage, since it's connected to earth, it's going to be 0. And when I look at the V minus voltage, I would say it is this potential, which is either V out minus voltage of this resistor or V in plus voltage of this resistor. So to find V minus, I did V in plus voltage of this resistor by using a potential divider rule. And the voltage of this resistor would be R2 divided by the sum of two resistances, R1 plus R2. And then the difference of voltage over here, which is V output minus V input. So I repeat myself, in place of V plus, I put 0. In place of V minus, this voltage is going to be V in plus the voltage of this resistor. And the voltage of this resistor is going to be R2 divided by R1 plus R2 multiplied by the difference of voltage between these 2 points, which is V out minus V in. So guys, I mean, from here onwards, it's more of the algebraic simplification. So if you might notice in this particular step, I have just multiplied A naught with minus and just copied this thing as it is, where I have multiplied V output with this as well as V input with this. Basically, I mean, before I tell you the algebraic simplification, because you don't have to do it exactly the way I'm doing it, but before I tell you the algebraic simplification, you know, we're trying to find out the gain of the operational amplifier by doing this connection, and gain is the ratio of output and input. So this is V naught, and this is V naught, this is V in, and this is V in. So algebraically, what I'm trying to do is that I'm trying to separate the terms of output and input on these separate sides so that I can try and rearrange to get the ratio of output and input. For that, I mean, if you notice in this particular step, I haven't done much. I've just multiplied A naught by minus, and I have multiplied these two terms separately to get this particular step. My entire target is to get the ratio of output and input. So again, what I did after this is that I multiplied A naught to all of these three terms, and then I shifted the V output term on the left hand side. So you could see minus A naught into V naught into R2 over R1 plus R2. When it shifts on the other side, it becomes plus A naught V naught R2 over R1 plus R2. And this minus A naught V in stays on the right hand side, and minus A naught into minus V in into R2 over R1 plus R2 is this term. So it's like you have output terms on the left hand side being gathered and the input terms on the right side being gathered with the same target in mind, and that is that you want to find out the ratio of output and input. Okay. And in this particular step, I have divided this entire thing by A naught. So since I've divided the entire equation by A naught, this becomes V naught over A naught. There's an A naught here already, so if I divide it by A naught, it will cancel. If I divide this by A naught, it will cancel. And if I divide this by A naught, it will cancel. So this is how the equation would look like if I divide the entire thing by A naught. Okay. So now once I divide this entire thing by A naught, and the whole purpose of doing that is one of the mathematical identity that 1 upon infinity is equal to 0. So I have only, since A naught is ideally infinity, so 1 upon A naught ends up becoming 0. So V output over A naught becomes 0. And hence, in the next step, I don't write this particular term. So if you notice in the next step, I have just copied this entire thing again by taking V in common from these two terms. And I haven't written down this term. That's because 1 upon A naught is infinity, and 1 upon A naught is 0. So this entire thing becomes 0, and that's how we get this. And you might notice, I mean, I've done this entire thing to get the ratio of output and input. So now I'm going to shift this input on this side so that I can get the ratio. And I'm going to divide this R2 over R1 plus R2 onto the right hand side of the equation. So R2 upon R1 plus R2 divided by R2 plus R1 upon R2 becomes 1. And 1 upon R2 divided by R1 plus R2. This is just like shifting this term, dividing to both the terms on the right hand side. So this upon this becomes 1, and this upon this becomes 1 upon R2 upon R1 plus R2. So, I mean, I told you my target was, right from here, I told you my target was to get the ratio of output and input. And that's why I did all of this entire algebraic rearrangement. So you could have, I mean, done it slightly differently in your own way, but the main purpose was to get the ratio of output and input, which is the gain of the operational amplifier. Okay, and then this entire thing would simplify as R1 plus R2 over R2. And then I have splitted this as well. R1 upon R2 is written as here. R2 upon R2 would become 1, and 1 and 1 would cancel out. And it just simplifies to minus R1 upon R2. So one thing is that when you look at this formula, this tells you that, first of all, the gain is entirely dependent upon the external parameters and not the internal parameters of the operational amplifier anymore. And secondly, you can control this gain. This is R1 upon R2. So if you can choose the resistance of your own choice, if you could choose these resistors of your own choice, then you can control the gain. Like for example, if you take R1 as 100 ohms and R2 as 50 ohms, so 100 upon 50 becomes 2. So you can, that way the gain of the operational amplifier is going to become 2. If you choose R1 as 150 and R2 as 50, then 150 upon 50 gives you 3. So that way the gain would be 3. This is such an amazing thing about these operational amplifier circuits that I told you there's a very, very complex internal circuit that we don't discuss at our level. But somehow we don't even need to do that because whatever is the internal circuit does not affect your gain. You can control the gain by the external parameters. By choosing these two resistors, you can choose what gain you want of the operational amplifier. So one thing is that gain has reduced, and second thing is that the gain has become more of a control parameter of ours. We can choose what gain do we want. depending upon what resistances do we connect externally. So guys, does that make sense? All right, that's perfect. So, so guys, that's basically one thing. I mean, what I'm trying to say is that if I just make this socket like again and let's say I have this is plus 9-volt battery and this is minus 9-volt battery, and this is let's say 100 kilo ohms, and let's say this is 50 kilo ohms. And if I want to just make a table of output and input for this particular circuit, so if I would say that I have input and I have output, let's say the input is 2. So guys, what's the gain of this particular circuit? Very good. Well, I mean, not 2, but it's -2. The gain of this circuit is -2 because I told you this is minus R1 upon R2. And that's one of the reasons why it's called inverting operational amplifier, because the gain is negative. V output over V input, which is the gain, is equal to minus R1 over R2, which you already got as -2, and that means you're saying that V output over V input is -2. So what is V output? That's -2 times V input. And I said V input is 2. So it becomes, it's minus. So guys, if input is 4, what do you think would be the output? It is minus here. So guys, and then if I'd say the input is 6, what would be the output? Yes, it would saturate. But I mean, I can't get an output of -12 with supplies as big as 9 and -9. So since it's going to saturate, so it cannot give you an output that's bigger than 9 volts or -9 volts. So the output is going to be -9 volts. That means your output is going to be -9 volts. But if you keep on increasing it, if you make it 8, it'll stay -9. If you make it 10, it'll stay -9 because output cannot go above -9. So if I would just say that I want to see how output is compared to the input. So guys, this is how the response of an operational amplifier is going to be like. It's an inverting operational amplifier. A gain of -2 means that if the input is, let's say this blue line is representing an input and the red line representing the output. This is the output. So the best thing about this is that the gain has been controlled, and the gain is quite small. It's -2. So a 2 would give you a -4 output. A -2 would give you a +4 output. if the input is 4, you get -8. If input is -4, you get +8. So you also see that the reason it's called inverting operational amplifier is because it inverts the input. A positive gives you negative, and a negative gives you positive. So you can also say that output and input are 180-degree out of phase. But the output that you're gonna get obviously might even saturate, and this is where you get a clipped output. That's because the output cannot go below -9 and above +9 because those were your batteries, those were your power supplies. So Even this saturates, but it has lesser chances of saturating as compared to the open loop circuit, where in open loop circuit, the gain was extremely high and was always saturating. So somehow with the negative feedback, what you've achieved is that you have a greater operating stability, you have a control gain, and you have a greater bandwidth. Greater operating stability is because your output is pretty much more stable. Instead of going to a plus saturated or a minus saturated mode, it's a controlled output. And the other response is something you have to remember, that it has a greater bandwidth, because I mean the gain does not get affected by the frequency of the signal, which was happening in case of open loop. If you might remember, I go back to where we discussed the open loop circuit. I said that for higher frequencies, the gain would reduce, but that doesn't happen in case of the negative feedback circuits. So the gain would remain same for even higher frequencies, and obviously it wouldn't saturate. So that's the advantage of a negative feedback of an operational amplifier. So we got gain as minus R1 over R2, and with this gain, we know that the gain has been controlled and has been reduced. And we will get a bigger output, but we will get a proportionate bigger output. So the operational amplifier would actually start up doing what it was expected to do. So, I mean, if I'm using an operational amplifier in situations where I have to, let's say, use it in microphone, so I would want the output not to be saturated. I would want the output to be sort of in proportion to what the input is, so that it would be similar to the input. So I mean, if you want to make sure that it doesn't get clipped at the edges, so you can connect power supplies which will cover up the voltage. Like, you know that the maximum voltage is F12 and minus 12. So instead of using 9-volt power supply, you can use 12-volt power supply, so that it wouldn't saturate and you wouldn't get a clipped output. But somehow, this is what a negative feedback would do for you. It will control the gain, and it will make the gain smaller, so the output is more proportionate to the input, and operational amplifier does what it's meant to be doing. The derivation of gain is part of your syllabus, but I've always felt that this way of acquiring the gain is more logical. But the good thing is that this is a longer algebraic working, so examiners never given anything where you have to forcibly do it like this. So there's another way to get the gain. The derivation is part of your syllabus, but this is something you can always do in derivation. So this is quicker, shorter approach. For this one, you have to do a lot of assumptions. One is that you remember, if you look at the original formula of the operational amplifier, two things you have to just make note of. One is that, you know, looking at the original formula of the operational amplifier, the gain is too high, infinite to be very exact. And that means that if V plus is higher, the output would be plus saturated, and if A minus is higher, the output is going to be minus saturated. And we've already seen the response of an operational amplifier that mostly it's not going to be saturated. So if it is not going to be saturated, then I would know that V plus and V minus must be nearly equal to each other. So that's one of the assumptions that we're going to make, that if V plus, and by the way, if you look at these circuits, it's the same circuit being drawn differently. So the first thing you need to identify is that V plus and V minus should be nearly equal to each other. Otherwise, the operational amplifier would saturate, looking at the original formula. So since V plus is 0, V minus should also be approximately 0. And that's why we use a term for it. We start calling it virtual Earth, which is because it's not actually connected to Earth, but to prevent saturation, it should be nearly equal to 0. So it should also be nearly equal to those 0 volts, and hence it should be equal to Earth, and hence it's called virtual Earth. And the other thing, guys, is in relation to the fact that if you might remember, one of the assumptions of the ideal operational amplifiers was that the input impedance is infinite input impedance. And when I was explaining you this, I said that that means to say that there's negligible current or zero current going into or out of the terminals of the input terminals of the operational amplifier. So that's the other thing that we're going to be using over here. We're going to say that no current moves in or out of the operational amplifier. So the current going into the operational amplifier is going to be zero. So if you connect an input, then the current would flow and would take this path. And if you look at this closely, this current I2, and we've already said that this voltage would be zero. So this will be V in minus 0 over R2. Its potential difference over resistance is equal to current. And this I1 must be equal to 0 minus V out over R1. So that's 0 minus V out over R1. And then it's a simple rearrangement. This is something that has come too often in exam. And this is a direct approach towards getting the same result. So the gain is still minus R1 over R2, the ratio of the two resistances.